Pawlyn. It's Michael Pawlyn, who I'm delighted to introduce to you. And I think what Michael's going to talk to us about in a sort of diverse way actually links into a lot of the ways in which we should be thinking about how we're trying to engage with and raise the debate levels around why to do business continuity, crisis management, risk management. So let me tell you a bit about Michael. Michael was one of the lead architects behind the Eden project in Cornwall. Anybody been to the Eden project in Cornwall? Yeah, Michael did that. Now, he's treating that as a blueprint, as he believes there are huge gains to be made from learning how the natural world works, especially in the effort to slow down the effects of climate change. And again, climate change is something that we obviously talk about a lot because, you know, with severe weather incidents and so on, that's becoming quite a big focus in the world of business continuity, whereas traditionally it was loss of IT and loss of buildings. Michael's work includes a carbon-neutral method for regenerating waste and the revolutionary Sarah Forest project, which mimics the Namibian fog-basking beetle's ability, I can't wait to hear about that, to create its own fresh water. Michael represented Grimshaw as a founder member of the UK Green Building Council and is a member of The Edge, the environmental think tank. One of the things that took my eye, though, in Michael's biography was a client comment, which I think is what linked what he's talking about in the day jobs that we have in engaging senior execs into business continuity and the way in which we go about it. The comment was, Michael inspires audiences to look at the debate with imagination rather than doom-mongering. And I think that that's something, if we've moved on from the doom-mongering stage of trying to make people want to do something about improving their organisational resilience, then we're certainly on the right track. But I'm very interested to hear Michael's side of this and see how we can make some links into the type of work we do from the subject matter that he's involved in. So please welcome Michael Pawlyn.
Thank you. Well, thank you for that introduction, and indeed I'm not Michael Pawlyn, but I am a fan of Monty Python. So now for something completely different. As you just heard there, I do prefer to talk about solutions than gloom, and I often find there's a very unhelpful dichotomy between some of the Greens on one side who say, you know, we're all doomed, and some in the fewer now, but some in the business world who say, really, we've got no problem, we just need to carry on. And what I advocate is taking a very cool, calm look at future challenges and then devising solutions to those. And the kind of challenges I'm talking about are things like climate change, resource shortages, food, energy, and water security. And the source of solutions that I find the most useful in this is a discipline called biomimicry, which is about looking to nature as a source of inspiration for new solutions. And I can give you a couple of quick examples of what I mean by biomimicry. Imagine, or think of a spider and spider silk. Now, a spider produces 6 different types of silk, which it weaves together with its back legs into a fiber tougher than any fiber humans have made to date. The nearest we've come is with a fiber called aramid fiber, or Kevlar by another name, which is what we make bulletproof vests out of and so on. And it's worth looking at how you make Kevlar, an aramid fiber, because what you have to do is you take petroleum, you boil it in sulfuric acid at about 750 degrees centigrade, and then following the principle that if brute force doesn't work, well, you clearly haven't used enough, you then pile on extremes of pressure to get the molecules into place. Out of that, you get your fiber and a huge amount of toxic waste. So extremes of energy, extremes of pressure, loads of toxic waste, and all that to do the same as a spider does at room temperature with raw materials of dead flies and water. It does suggest we've still got a little bit to learn. And then this example, this is a beetle. I'll come to the fog-basking beetle, that's later. This is the bark beetle, and this can detect a forest fire at roughly 80 kilometers away. Human-made fire detectors, you might be able to see one or two on the roof, they have a range of about 8 meters. So this is 10,000 times as sensitive, and what's more, it doesn't need a continuous connection back to a power station burning fossil fuels. You might wonder why the hell a beetle would fly towards a fire. Well, it actually flies to where the fire has just passed through, and it lays its eggs in freshly burnt wood. And there's a kind of popular science explanation for why it does this, which goes roughly like this. When it gets to where the fire has just passed through, all its mates are there, it can have unlimited sex with no predators around, and you don't get much better than that in the beetle world. But the important point is that it's an example of an adaptation to a very specific niche. And if we could learn how it does that, then there's a very real chance that we could make much more effective, much more efficient fire detectors. And another example, this is a rainforest plant that we've looked at. It's called Anthurium warraquinum, and it lives in very low light conditions, so the rainforest floor, and it's found a way to survive by it's evolved this covering of lenses over its leaf, and those lenses are able to focus the very low levels of diffuse light onto the chloroplasts which photosynthesize. And so the overall message with these examples is that nature could be viewed as a kind of storehouse of amazing design ideas. And all those design ideas have benefited from a 3.8 billion year research and development period. And to make things even better, all the faulty products have been withdrawn from the marketplace. So given that level of investment, it kind of makes sense to use that and to learn from nature to devise new solutions. And just about all those solutions will be well adapted to exactly the kind of challenges that we need to face. There'll be resilience, there'll be zero waste, non-toxic, very resource efficient, running on current solar income, and so on. And I think that over the course of the next few decades, there are three really big challenges that we need to address if we're to move from the industrial age to what I would call the ecological age of humankind. The first is achieving radical increases in resource efficiency, so doing far more with far less. The second is shifting from a linear, wasteful, and polluting way of using resources to a closed-loop model, in which all the resources are stewarded within closed-loop cycles. And then the third one is shifting from a fossil fuel economy to a solar economy. And if we choose to embark on these three interlinked journeys, then, in my opinion, there is no better source of solutions than biomimicry to deliver the kind of solutions that we need to really prosper in this age that we're entering. And you can apply biomimicry to just about any functional challenge. I'm going to be talking mainly about buildings because I'm an architect, but at the end I will touch on how biomimicry can be applied to really quite different disciplines. So let's start with the first big challenge, the idea of achieving radical increases in resource efficiency. And this was very much in our minds when we were working on the Eden project. We had a really difficult challenge. We had to build the world's biggest greenhouse in a quarry that was still being mined. And it was ideas from nature that we turned to at pretty much every stage in the design process. So ideas of spherical geometric structures like this pollen grain, the marine microorganisms called radiolaria, even carbon molecules show exactly the same highly efficient spherical structure. And that's what led us to develop the structure that you can see on the Eden project. And what we found is that we got into a kind of positive cycle in which one breakthrough facilitated another. So with such we had a very lightweight membrane on the outside of the building, and that produced savings in the steelwork. With less steelwork, we were getting more sunlight into the building, and with less overall weight in the superstructure, there were big savings in the substructure. So at the end of the project, I worked out that the weight of the superstructure was actually less than the weight of the air inside the building. And if we were to go through that process again, learning further lessons from nature with better building technology, I'm pretty confident we could take that steel weight down even further. And the structural solution that we developed from looking at these natural examples was actually far more resilient than a more conventional solution. A more conventional solution would probably have just sort of linear arches spanning from top to bottom. This one, if one of those steel members broke, there are lots of other paths that the load could take to get safely down to ground. So there's quite a high degree of redundancy in this system. And that Eden Project, I think, is a pretty good example of how you can use nature to develop a completely new approach to what was a fairly standard building type. And what we developed there was something that cost a third of the price of a conventional glass roof. So now I'm going to turn, still with the subject of radical increases in resource efficiency, I'm going to turn to a more conventional building, which is an office building. And this is one that we've been working on over the last year or so, basically using biomimicry to rethink office design from a completely blank page. There have been some very good sustainable offices built, but I had a hunch that if we use biomimicry, we could go beyond what I would call a sustainable paradigm to achieve a more restorative paradigm. And with buildings, obviously you can make them resilient by having large amounts of backup systems, backup lighting, a backup generator, backup air conditioning, and so on. But I think it's much more ingenious if you can design it in a way that designs out a lot of those systems. And these were the challenges that we set ourselves after the first workshop. We wanted to achieve a minimum 10% increase in productivity for the people inside the building, for the building to be, as far as possible, passively self-heating and cooling, entirely lit with daylight, for the building to be a net producer of energy, and for the air coming out to be cleaner than the air going in. And I would argue that those last three are actually doing what I said about going beyond sustainable to achieve a restorative aim. So let's look at the first of those, light. Now, light is pretty much a precondition for all life forms on Earth. So it's not surprising that you can find really quite striking examples of how light is gathered and distributed in biology. And we actually had a biologist, one of the best biomimicry professors in the world. We had him as part of our design team. And this example, this is called a spookfish. And the spookfish has these eyes with amazing mirror structures, which are able to focus low-level bioluminescence onto its retina. Another one that we looked at with our biologist was the stone plant. Now, this is a plant that lives in deserts, and for reasons of temperature control, most of the plant is below the ground to steady the temperature. And then it has what you could call a roof light in the top that brings the light into the basement where the photosynthetic matter is. A third one we looked at is called the brittle star. And this is a starfish that lives roughly 500 meters below the ocean surface, where light levels are incredibly low. And like that plant I mentioned a few minutes ago, it has evolved a covering of lenses over its skin, near optically perfect lenses, which can focus and detect very small amounts of movement. And so it's able to detect a predator long before the predator sees it. And I think what we found with all of these examples is that they all encouraged us to think much more creatively and deliberately about how we would bring light into the building, trying to create a building that was largely or as close as possible to entirely day lit. And a fairly conventional way of thinking about daylight in office buildings is to just think about the right distance between the windows. And in this country, there are quite often buildings that are very deep, 30, 35 meters deep. And you know then it's going to be an energy-intensive building because it's going to rely on artificial lighting and a lot of air conditioning. We concluded that the right distance was about 12 meters. So no one would be further than 6 meters from the nearest window. And then we thought about what kind of building forms this suggested. One approach would be to just take these narrow floor plates and stack them up into a tower. And that would work fine if it was a dense urban location with high land values. We were probably going to have to deal with an out-of-center location. So we looked at two other types. One was a kind of donut ring, where you have a central atrium. And a third one was a more linear approach, where you have two linear blocks of office buildings, and then you have a linear atrium. And it was the third one that seemed to work best when we actually analyzed the light levels. And looking at those light levels in plan, what we found is that we got a kind of curved pattern of shading a lot towards the middle of each block. And that was because of the shading effect of the opposite block. So the next design move was to bend those floor plates so that we would get a very even quality of light all the way along. And this produced two further challenges. One was that narrow floor plates aren't particularly good for creative clusters of people. And the second was that we were probably going to have to deal with a rectangular site. And this really wasn't making very efficient use of a rectangular site. So then we decided to elaborate those plan forms in the same way that biological forms are often elaborated to optimize the surface area. And we produced this plan form here with these undulations. So we still had no more than 6 meters from the nearest window, but now we were getting much better facilities for creative clusters of people. You need a slightly bigger space for effective working. Then we looked at the way daylight worked in the section. And what we found is that we were probably going to be getting more light than we needed at the top and not enough light further down. So we looked at the possibility of actually harvesting light at the top. Using the trick from the Anthurium warraquinum, we wondered whether we could actually focus that light into fiber optics and then conduct it down to lower into the building. And that's perfectly possible, but that was something we had to sort of park as a separate research project. There wasn't the time to do that within the constraints of this study. But what we did conclude is that there could be an advantage in tapering the building forms and incorporating a large-scale mirror like the spookfish eye in the atrium. And that mirror would bounce light deeper into the lower parts of the building. And then thinking about what we might do underneath that big mirror, we thought this was a great opportunity to include a meeting room, a really dramatic meeting space with some of the qualities that you see in some of Ken Adams' designs for the James Bond film sets, and this one's actually for Dr. Strangelove. We like James Bond in my office, so that was good fun. And then one of the secondary benefits of designing for high levels of daylight is you can incorporate a whole range of plants into that space. And NASA did quite a bit of work on self-contained resilient ecosystems. And they found that these 3 plants in sufficient quantities can deal with nearly all the contaminants that you find in an indoor environment. Money plant produces a lot of oxygen during the day. Mother-in-law's tongue produces a lot of oxygen at night. The areca palm is very good at taking out volatile organic compounds. And all 3 are very good at deionizing the air and reducing dust levels. In a test version of this in India, on a 5,000 square meter office, they've achieved really quite remarkable results. As much as a 20% increase in productivity, a 50% reduction in headaches and eye complaints, even a measurable increase in blood oxygen. So now turning to another aspect of the building, essentially we looked at it in functional terms and addressed each one and tried to use biomimicry to develop new solutions. So we saw how the basic building form has already been determined largely by daylight. And so the way we used biomimicry on the structure was to think about how we could use an absolute minimum of materials. In biology, you could characterize biological structures by saying that materials are expensive and design is cheap. And what I mean by that is that you often get really very complex structures that achieve, in biology that is, that achieve remarkable efficiency by putting the material exactly where it needs to be. So this is a section through a bird skull. And what you have is layers of incredibly thin layers of bone connected together with struts and ties. So it's like a combination of dome technology and space frame technology, all in a humble garden bird. Another one we looked at is the cuttlebone from a cuttlefish, and that's quite similar. You have thin layers of bone connected with these undulating walls. So again, a very strong structure with a minimum of materials. And what we did with our office building was that we analyzed a fairly generic floor structure of a slab and columns, and we looked at it in terms of which bits of that structure were working hard and which bits were really quite redundant. And all these bits that I'm shading in dark here, these are the bits that are structurally redundant, the centers of the columns, the centers of the slabs. And so if we were to follow the shape that it wants to be, it would probably look something like this. We would have slightly deeper floor plates in the middle, we'd have hollow columns, and then in the middle of the floor plates, we would take out some of that mass with voids. And then there's a chance that we could actually connect the air cooling system up to all these voids in the floors. And by doing that, every molecule of that building would be doing 2 functions, a structural function and a thermoregulation function. And this is entirely possible with the existing technologies. So what we often do is we use biomimicry to identify the absolute ideal, and then we come back from that to something that is achievable with current technologies. And the real breakthrough technology for us would be when 3D printing and 3D manufacturing has advanced to the point where we can manufacture building components. Because then we can manufacture very complex and highly efficient forms with no cost penalty. In fact, we would actually achieve major cost savings because we'd be using less resources. Up until now, it's been difficult to do that because complex bits of structure tend to be more expensive. But 3D printing has the potential to change all that. Now moving on to thermoregulation, what we saw in that last example was that pieces of structure often become more efficient when they're hollow, if you put the material where it needs to be. And in biology, hollow structures are nearly always used for something else, for conducting gases or liquids around the organism, or in our case, say in the case of our spinal columns, conducting information. Nerve cells pass all the way from our brain through our spine, connecting up our body. And this made us think about the idea of connecting the building into the ground underneath. The temperature of the ground a few meters below the surface is a very steady temperature all year round. And that's a trick that you can see in examples like ground burrowing animals. They use that to modify the temperature in their burrows. And the real masters of this are termites. We're used to kings and queens being quite high maintenance, but arguably there's no more high maintenance monarch than the queen termite, who insists on temperatures of plus or minus 1 degree in the royal chamber, even though the temperature outside is changing by as much as 40 degrees. So what we proposed was that we would create this network of pipes under the ground, and then we could use the steady temperature of the ground to connect up into the building, so benefiting from free heating in winter and free cooling in summer. The final bit of this jigsaw puzzle on the office building is the external envelope. And this got a little bit complicated, so I've summarized here what we were trying to do. We wanted to achieve high levels of daylight for human health and to reduce energy consumption. But daylight varies enormously from 0 at night, obviously, to as much as 100,000 lux on a really bright day. But in the working environment, you want a fairly steady level of illumination. And we also need to emit light but not lose heat, and that can be challenging. So on that last one, we looked at high technology insulation products that also emit light. This is called aerogel, which was developed in the space race, incredibly lightweight, very insulative, and very light translucent. And it's really come down in price a lot, from absolutely extortionate to just downright unaffordable. So we moved on to some other examples. Polar bears actually have hollow hair fibers, which are part of what insulate the polar bear. And it was partly that helped us develop a translucent insulation system. And then what we needed to do was to create a kind of covering over this building. Let's say it's a covering of leaves, which could move to emit exactly the right amount of light. The ideal, we reckoned, was to allow exactly the right amount of light in and to convert all surplus light into electrical energy. Now, that means photovoltaics. It also means things that move, and both of those tend to be expensive. But you can make it a lot cheaper by having a large number of small identical pieces of solar cell, and by making those just move between two positions. If they just move between open and closed, that's much cheaper than something that moves through a whole range of positions. And then we looked at examples of movement mechanisms in biology. This is called the sensitive plant. When you touch it, the leaves close up. Beetle wings, quite interesting examples of things that fold up into a very compact form. We also looked at folding patterns in leaves and in flower petals. And we also used lessons from shells to develop a glazing system that used about 50% of the amount of glass of a conventional solution. And this is how the scheme looked at the end of the commercial feasibility study. We did a concept study first, and then we did a commercial feasibility study to prove that this could be built for a realistic cost plan that would still allow the developer to make a profit. And you can see that most of those ideas that we started with are still there: the undulating plan form, the large-scale mirror in the middle with the meeting room underneath. And what this is as a building is something that I would argue would be extremely resilient. You could have a major power cut where this was built, and this could continue functioning almost indefinitely. It would need a certain amount of reserve batteries so that it could light the workspaces at night. But during the day, it would be almost entirely day lit, is generating most of the energy it needs, and so on. And I think the benefits go beyond that. I think it's also it would be an extremely enjoyable workspace for people to work in. I think they'd be much more productive. And we felt that the economic benefits of this, possibly we hadn't spelt these out as well as we could have done. So we put together this kind of back of the envelope calculation to show to the client. Now let's say the building costs 90 million Swiss francs, and this was to be in Switzerland. So let's say there were 3,000 people in there on a salary of 100,000 Swiss francs a year. That means the annual salary bill would be 300 million Swiss francs. Now, if we could achieve a 10% increase in productivity, then that would be worth 30 million Swiss francs a year, which means the building would pay for itself completely in just 3 years. It can be quite difficult to persuade clients of the validity of this approach, but I think we are now moving beyond the idea of just making sort of small-scale energy savings and actually looking at brand value, quality of life, and people's productivity. And I think increasingly we will see these kind of arguments accepted by clients. And increasingly I think we'll see the argument for resilient design as being increasingly important. So that was all about radical increases in resource efficiency and how we can use examples from biology to rethink existing challenges. Now I want to look at the second big challenge, which was the shift from a linear, wasteful and polluting way of using resources to a closed-loop model, similar to ecosystems. And there are some industries and some industrial parks that have been set up based on this idea. They've co-located industries so that the waste from one can become the nutrient for something else in that system. The example I like the best is a project called the Cardboard to Caviar project, which I think describes what this is about extremely effectively. This was set up by a guy called Graham Wiles, and what they did is that they collected cardboard from shops and restaurants. They then shredded that and they sold it to equestrian centres as horse bedding. When that was soiled with manure, they were paid to collect the cardboard and manure. They put it into wormery composting systems, which produced lots of worms, which they fed to Siberian sturgeon, which produced caviar, which they sold back to the restaurants. Which is quite nice because it's turned this linear, wasteful system into a closed-loop system that also creates far more value because they were paid at various stages. They were paid for the horse bedding, they were paid to take away the manure and cardboard, they were paid for the fish, paid for the caviar, and so on. And I'd been using this example in talks for probably about 3 or 4 years, and then I was invited to teach on an intensive course about biomimicry. So I thought it was time I actually found out the full story. And I went up there and met Graham Wiles, and he very generously showed me all about the project. And in many ways, the longer story is more interesting than that summary. And I think it's got some interesting lessons for resilience as well. Because when he started, it was just the first part of that. He was involving people with disabilities to shred cardboard, and they were selling it to the equestrian centres. And then the horsey people said, okay, well, what do we do with this waste cardboard and manure? And Graham Wiles said, leave it with me, I'll have a think, I'll think of something. And his first idea was to set up a wormery and supply a fishing bait supplier with worms. So he did that, and then at the 11th hour, the fishing bait supplier backed out of the deal. I don't know, the global market in worms had collapsed or something. And so Graham said, all right, well, damn you, I'm going to cut out the middleman and set up my own fish farm. And this time, he started working with reforming heroin addicts, pretty difficult kids who were causing a lot of problems in terms of crime and costing the local authority as much as £100,000 per addict per year on rehab schemes with a 95% failure rate. Graham Wiles has achieved a 65% success rate at getting them off drugs and back into something more productive. Now, what they found in the first year was that the fish weren't putting on enough weight in winter because the water was too cold. And by this stage, they'd been given quite a big bit of land by Yorkshire Water. And this land was formerly industrial land in pretty poor condition, but the waterworks gave them unlimited quantities of treated fertilizer sludge. So they used that to restore this industrial land, and they planted willow biomass. And that was used to power a biomass boiler, which made the fish happy in winter. And then Graham found that he was having to spend a certain amount of money on fish food to supplement the worms. And he didn't like this. He didn't like anything leaking out of his system. So he got the kids growing vegetables so that they could make their own fish food. As it turned out, the kids ate all the vegetables, but in many ways that was a good thing, because prior to that they were just coming to the site every day with a can of Coke and a Mars bar for their lunch, so little wonder they have certain sort of behavioral problems. So now they were learning about healthier food. The next thing is that they restored more industrial land and they planted orchards, so that was another product to sell back to the shops and restaurants. Then they redesigned the water treatment system from the fish tanks to use salad crops to take out the excess nutrients. So that was another product for the shops and restaurants. And then they found there was a bakery nearby that was producing loads of moldy bread. It was chucking tons of moldy bread every week into landfill. And Graham discovered that you can raise maggots on moldy bread with none of the smells of meat-based production. So that was another foodstuff for the fish. And a final part of this, which is not on the diagram, is that he's recently set up a smokehouse to add value to the fish. And this time he's worked with ex-service personnel. And a shocking number of ex-service personnel, when they come back from conflict zones, they end up in prison because they often come back with post-traumatic stress disorder. They find it difficult to adapt to civilian life. Their relationships break down. They end up in prison, which is a bit of a slap in the face after the kind of sacrifice they've made. And what I think is fantastic about this scheme is that Graham Wiles has been inventive with waste in every sense, not just physical resources, but with what is arguably the most deplorable form of waste, and that is underutilized human resources. He's managed to re-involve 3 marginalized groups, people with disabilities, reforming heroin addicts, ex-service personnel, into a system that is truly regenerative and productive. And just as real ecosystems increase in diversity and resilience over time, there's a real sense with this that the more it grows, the more the number of possibilities increase. Turning waste into value, restoring land, enhancing biodiversity, involving people in a productive system. And I think that project actually satisfies nearly all the criteria of a real ecosystem. So if we compare the characteristics of typical human-made systems, we find that ours are simple and disconnected, whereas biological systems are complex and interconnected. Ours tend to be linear and wasteful, whereas biology is closed loop and zero waste. Ours tend to be resistant to change. We use long-term toxins, nature doesn't. Ours are fossil fuel dependent. Nature runs on current solar income. Ours are often engineered to maximize one goal, whereas ecosystems have evolved to be an optimized overall system. Ours are extractive, biology is regenerative. And I think if you look down that right-hand list, that's actually a very good summary of where we need to be heading to rethink our industries, our cities, our processes over the next few years. And most of those would enhance the resilience of the system as well. So we've been playing with some of these ideas, partly based on the Eden project, partly based on that cardboard to caviar project. We wanted to create an urban greenhouse with a restaurant inside it. And this one it already exists. This is in Holland. It's called De Cas, where you sit inside a productive greenhouse and there's no menu as such. You just have whatever's in season, and it may be as little as an hour from the food from being on the plant to being on your plate. So we thought that was quite fun. And in our urban greenhouse, we also wanted to incorporate a number of other systems. We wanted to bring together a range of systems so that the waste from one becomes the nutrient for something else in that system. So we proposed incorporating a biodigester that could deal with all the biodegradable waste from the local urban area, turning that into energy and fertilizer. We proposed a water treatment system that uses plants and microorganisms to treat wastewater. We obviously had to have a fish farm after the fantastic cardboard to caviar project. This would be fed with vegetable waste from the kitchen and then would supply fish back to the restaurant. And because this was to be an urban location, we proposed a coffee house. And the spent grains from coffee are actually an ideal substrate for growing mushrooms. So we wanted to bring all these together within one building to form a mini ecosystem. And just for fun, we chose a really challenging site. Some of you may know this. It's Old Street Roundabout. It's an absolute eyesore. You've got this roundabout that no one can get to with 4 lanes of traffic around it. But since the congestion charge, most of the traffic actually comes from here and ends up going up that way. So with a fairly small amount of replanning, we could reclaim a public space for people, and we could create this scheme that would reconnect people with food, energy, water, and waste while transforming major problems into closed-loop opportunities. And I think there's a great opportunity to completely rethink the whole metabolism of our cities and look at those linear flows and look at those waste sources and look at them as opportunities. Opportunities to create more value and eliminate waste. So the final project I'm going to talk about is one that picks up on this idea of shifting from a fossil fuel economy to a solar economy. And I think a big part of addressing our energy challenges will be to rethink deserts. It's also about creating renewable energy systems in our own country, connecting those all up with high voltage DC power lines so that we're creating a highly networked, resilient system across Europe. But most of the kind of informed predictions are that we would really struggle to meet all our own needs with renewable energy in our own country. And there's a great opportunity to connect into solar systems in North Africa. And to give you some idea of the potential energy, it's quite easy to work out the amount of energy we receive. And the Earth receives roughly 7,000 times as much energy as we use in all forms. So we get 7,000 times as much energy from the sun as we currently use from conventional sources. So that statistic of 7,000 to 1, I'm not suggesting this shift is going to be easy, but that statistic does at least suggest that it's possible. And actually, it's a challenge to our ingenuity. So on this project, we wanted to propose a major solution to climate change, but in contrast to the way that some environmental schemes are developed, we didn't want to just look at one problem at a time. We actually wanted to develop an integrated solution that addressed multiple challenges simultaneously. And when we were looking at deserts, we were quite surprised to learn that a lot of the world's deserts were actually vegetated a very short time ago. So North Africa, when Julius Caesar arrived, what he found was this wooded landscape covered in cedar trees and cypress trees. And just to give you some idea of the abundance that existed at the time, when they had the opening party for the Colosseum in Rome, they transported 9,000 elephants, panthers, and bears from North Africa to fight Christians in gladiatorial combat. Say what you like about the Romans, but they knew how to throw a good party. I'm sure there's a Michael Pawlyn quote from The Life of Brian as well. The other interesting thing about that issue of vegetation is that most scientists agree that in terms of the evolution of life on Earth, it was the colonization of the land by plants that created the benign climate we currently enjoy. And this animation shows photosynthetic activity around the world over the course of a number of years. And what you can see is that the boundaries of those deserts actually move back and forth quite a bit over the course of each year, which for us raised the question of whether we could intervene at some of those boundary conditions to halt or even reverse desertification. And if you're into biomimicry and you're working in an extreme environment, then there's a lot that you can learn from, I'm going to skip that because I'd like to get on to the next bit. There's a lot that you can learn from the organisms that are already adapted to life in that environment. So this is the fantastic Namibian fog-basking beetle, which has evolved a way of harvesting its own fresh water in a desert. Now the way it does this is that it comes out of its hiding place at night, it crawls to the top of a sand dune, and because it's got its matte black shell, it's able to radiate heat out to the night sky and become slightly cooler than its surroundings. So when the moist breeze blows in off the sea, you get these droplets of water forming on the beetle's shell just before the sun comes up, tips its shell up, the water runs down to its mouth, has a good drink, goes off and hides the rest of the day. Not a great quality of life, but it's a clever trick, which is good enough for me. And the ingenuity, if you could call it that, goes even further, because over the back of the beetle's shell, there are a whole series of little bumps. And those bumps are hydrophilic. They attract water. And between them, there's a waxy finish which repels water. The effect of this is that as the droplets form on the bumps, they stay in very tight spherical droplet form, which means they're much more mobile than they would be if it was just a mist over the whole shell. So even when there's only a small amount of moisture in the air, it's still able to harvest that very effectively and get it, channel it down to its mouth. So it's a great example of what biomimicry can offer. It's an adaptation to a very resource-constrained environment. And it's reassuring to know that a lot of the resource challenges we're going to be facing over the coming decades will already have been solved in nature. And if we could learn from how those solutions have occurred and the mechanism, we can develop that into solutions that suit human needs. And we've used that to develop a new type of greenhouse for the Sahara Forest Project. And to explain the background, let's just look at some comparative temperatures. Let's say the temperature of the desert at night is about 30 degrees C, which is quite cozy. The temperature of outer space is minus 273 degrees C, which is a bit nippy. And then if you get a matte black surface, you can get that to radiate out to the night sky and lose heat by radiation. And that was the way in which the ancient Persians made ice thousands of years ago. They would put down a bed of straw for insulation, and then they would put a shallow ceramic tray on that with a matte black glaze, and they'd put a thin layer of water in it. And on a clear night, that black surface would radiate out to the night sky, and that was enough to form ice. So we're using a similar idea on our greenhouse. We've developed a greenhouse with a double layer roof. And what we do is we bring in seawater during the day and we evaporate that into the space to create a cool, humid growing environment, which is a much better growing environment for crops in hot, sunny deserts. And then at night, we lower the lower layer, we drop the lower layer of the roof, and we still bring in seawater into this roof space. And we use high emissivity surfaces, just like the beetle's shell, to radiate heat out to the night sky, and then you get condensation. Pure distilled water forming on those, which runs down to the bottom, and we can collect it and use that for irrigation during the day. When we think about biology, we often think about it as being all about competition. And certainly competition is important, but increasingly biologists have come to understand that in mature ecosystems, you're just as likely to find examples of symbiotic relationships in which organisms have evolved for mutual cooperation. So an important principle with biomimicry is to look for ways of bringing technologies together in symbiotic clusters. So we looked around for technologies that would work well with the greenhouse. And this is the one we settled on. It's called concentrated solar power, which uses mirrors to focus the sun's heat to create electricity. And the kind of synergies that I'm talking about, firstly, both these technologies work very well in hot, sunny deserts. Concentrated solar power, or CSP, benefits from seawater cooling. It's as much as 10% more productive. We can make use of all that waste heat to evaporate more seawater in the greenhouse and create more fresh water. And what is possibly the most interesting synergy is that the shade created by those mirrors makes it possible to grow a whole range of crops underneath that would not grow in direct sunlight because of the intensity of the sun and so on. So the idea at a sort of sketch concept level was that we would create these long hedges of greenhouses with concentrated solar power plants at intervals along the way. And at a large scale, it would look something like this. So it's a model for how we could create zero carbon food in some of the most water-stressed parts of the planet, abundant renewable energy, and we'd be able to revegetate areas of desert, locking up carbon, atmospheric carbon, in desert soils. Some of you might be wondering what we'd be doing with all the leftover salt. If we're evaporating a lot of seawater, you're going to be left with a lot of salt. And to biomimic, if you've got a lot of underutilized resource, you don't think, how the hell am I going to get rid of this? You think, what can I add to that system to make it more productive? So we've looked into the science of this quite extensively, and we found that you can actually extract a lot of useful compounds. The first thing to precipitate out when you evaporate seawater is calcium carbonate. We can actually use that to create building blocks. The next thing is magnesium chloride. You can use that as a drying agent in low-energy cooling systems. The next thing is sodium chloride. You can use that in a lot of industrial applications. And after that, you get pretty much every element of the periodic table. Now, we're not going to be able to extract the really trace elements like gold and uranium, but we should be able to extract a lot of the useful nutrients that were lost from the desert soils when Julius Caesar kind of broke that loop, and a lot of the nutrients from the desert soils were lost out to the oceans. So in a small way, we'll be able to close that loop and get those nutrients back into the desert soils. And over the course of the last few years, we've been developing this project. We've done a number of feasibility studies, and we've looked at a whole range of technologies that could be brought into this synergistic cluster. Technologies like algae for biofuels, halophytes, which are plants that grow in salt water directly and can produce food and fodder crops. We've also looked at how we would handle the salt and how we can evaporate the brine to get concentrated brine, which then makes it easier to extract the elements. And we're proposing, or we have used, these evaporator hedges, which create enhanced conditions for growth between. So that's furthering our aim of revegetating areas of desert. And really this has been a bit like a sort of plumbing diagram, looking at each of those technologies, looking at the inputs and outputs, and then working out how we could connect those up so that the waste from one becomes the nutrient for something else. Now, don't try and read that, but that is a kind of map of all these interconnections. And some people might look at that and think, well, Jesus, that looks hellishly complicated. And in a way it is, but it's nowhere near as complex as the interconnections of a real ecosystem. And I would argue that this is the kind of complexity that we need to embrace if we're really going to be creating resilient, highly productive, zero-waste systems. And with improvements in digital design tools, it's perfectly possible to do that. So on our project, the Sahara Forest Project, we built the first version last year in a very short time frame. This was built in time for the opening of the climate change talks in Doha. And this has allowed us to test all the main technologies, the greenhouse, the evaporator hedges, the concentrated solar power, and really sort of tune all those interconnections so that we're getting it to work as well as possible. This was the site, a completely barren desert site to start with. And this is the Emir of Qatar on the opening day looking at the external crops. And this is the quality of the produce that we managed to generate throughout the summer. Most greenhouses in Qatar stop production for 2 or 3 months in the summer. But with the evaporative cooling system, we were able to continue all the way through. And our next project we're hoping is going to be in Jordan. This valley here, the Aqaba Valley, is probably the best place in the world climatically for our technology. And interestingly, you could also argue that it's one of the best places in the world for what this scheme could do, because Jordan is actually a very insecure country in many ways. It's regarded as a sort of haven of peace surrounded by troublesome neighbors, but it's a very insecure country because it's one of the most water-poor countries in the world. It imports 97% of its energy. It's got a growing population and recently experienced its first food riots. So with a project such as ours, if realized at a reasonably large scale, we could really start to address the major energy, food, and water security challenges of a country. And in that sense, help secure the kind of peace that Jordan has enjoyed, even though its neighbors are somewhat more difficult. And over the course of the next few years, we'll be able to turn to examples from biology to carry on improving our project. So for instance, camel's nostrils, they're a miracle of water recovery engineering. The sand skink, that can swim in sand without suffering any scratches. Maybe we could learn from that to make scratch-proof coatings for our mirrors. The jewel beetle has created mirrored surfaces just using proteins at ambient temperature and pressure. The thorny devil, that can drink with its feet. If it's standing on damp ground, it has a network of capillary grooves on its skin. The water tracks up its skin to its lips, it licks its lips and looks rather pleased with itself, as it should. So all of these could help us refine our system. And I mentioned that I would touch on some other ways of applying biomimicry in quite different fields. And this is some work by someone called Paul Z. Jackson, who uses biomimicry and improvisational techniques with business. And he's developed this list, which is a comparison of the characteristics of a strategic plan according to a sort of conventional way and a more biomimetic way. So when you're forming a strategic plan, according to Paul Jackson, when you look at the future in a conventional model, that's regarded as kind of knowable, whereas in a biomimetic approach, you accept it as unknowable. The status of the plan, on the one hand, is definitive, but in a biomimetic approach, it would be provisional. The route on the first one is planned, on the second one is emergent. The biomimetic approach would look at possibilities rather than barriers and gaps. The biomimetic approach would have more of a direction rather than a specific goal. and the viewpoint would be more collaborative and interactional rather than expert, mechanical, and engineered. Now, this isn't really my field, so I can only offer a sort of opinion, but when I look at that, what I see on the right-hand side looks way more exciting than the left-hand side. The left-hand side looks pretty stodgy and conventional. The right-hand side is all about adventure. Oh, sorry, there's one more here in terms of skills. In the conventional model, it's planning and forecasting, whereas with biomimicry, it's more about improvising. Final example from a different field. This is from the field of transport. What you're looking at here is an organism called a slime mold. It doesn't sound very nice. It's a unicellular organism that forms a minimum distance network between sources of food. And some scientists in Japan did an experiment where they got a map of the Tokyo region, and they put small piles of food on the surrounding cities around Tokyo, and then they put a slime mold on Tokyo itself. The slime mold extended over this whole region, and then very quickly it formed a network around or connecting all the sources of food. And that was actually a minimum distance optimized network that almost exactly matched the railway network pattern for that region. The railway network had taken thousands of hours of engineering time to work it out. The slime mold did the same task better in 26 hours. It actually had a slightly more resilient solution because there were a few more redundant links that could cope with interruptions to that system. So I think increasingly over the next few decades, we're going to see biologically based algorithms that will help us design much more efficient, more optimized, and quite possibly more resilient solutions. And to draw to a close now, the kind of solutions that we've been looking at over the last 3/4 of an hour, these are really just a tiny fraction of what exists in a source book that we're only just beginning to understand. 3.8 billion years of research and development. That's what nature is. 3.8 billion years of brilliant solutions illuminated by previously unparalleled scientific knowledge, facilitated by previously unimaginable digital design tools. Designers have never had such an opportunity to rethink and devise solutions fit for the next billion years. And returning to those three big challenges of radical increases in resource efficiency, linear to closed loop, fossil to solar economy, of course, some people might scoff at the feasibility of a solar economy or the idea of zero waste, but we know this stuff is not the stuff of fantasy because the living world is proof of the possibility. And not just an ordinary possibility, but a wonderfully complex, abundant, and regenerative possibility. And that destination of the ecological age, I really believe that is close enough to touch. And biomimicry will be one of the best sources of solutions that will help us reach that. And that's a journey that we can all lead on if we choose to. As Margaret Mead said, never doubt that a small group of thoughtful, committed citizens can change the world. Indeed, it is the only thing that ever has. Thank you very much for listening.